Discovery of the electron.
Physics by the end of the 19th century was thought to be pretty well understood. Newtonian mechanics had been in place for several hundred years. Maxwell's equations were the culmination of work done over several centuries and showed that electricity and magnetism were really the same force. Thermodynamics. Heat is just another form of energy and can be transferred into mechanical energy, or mechanical energy can be transferred into thermal energy. The speed of light was measured, and it was found not to require a stationary reference frame or a medium, which was named luminiferous ether, to travel through. This helped lead to Einstein's special theory of relativity in 1905. So many physicists were comfortable, not all of them certainly, but many were comfortable that nearly everything had been discovered and explained. But then things started popping up, like the electron. About 150 years ago, cathode rays were discovered, and we'll soon see why the quotes are around the words cathode rays. No one knew what they were. Physicists working on the problem just knew what they could observe, which of course is always a great way to study. Do experiments, see things, do more experiments. What they saw was that when you put a high voltage on two plates inside a glass tube, making one plate positive and the other negative, then they would see a shadow cast on the glass behind the positive plate. Furthermore, the glass surrounding the shadow glowed. When more air was pumped out of the tube, getting closer to a vacuum, and the glass was treated with special fluorescent chemicals, the effect was enhanced. It would glow more. This seemed to mean that something was traveling in a straight line from the negative plate, the cathode, and that's over here. Here's your cathode. And you have a negative potential at here. And these rays, these cathode rays is what they called them, were traveling from the cathode to the anode. And a lot of times you'll see pictures, they use a Maltese cross here for effect. And then this positive plate, the anode, the metal cross, seemed to stop the rays, so you'd see a shadow over here on the other side of the glass tube. And as we just said, since the rays seemed to come from the cathode, they were called cathode rays. If you click on this YouTube website here, you'll see a nice demonstration of this effect. Once an experiment is performed, people want to explain what happened. So in this case, where we had these rays or something leaving the cathode, striking the anode, and then having the shadow appear on the other side of the glass, what's going on here? Well, light casts the shadow, so it could be light, or it could be a stream of invisible particles that are getting stopped by the anode, and only the particles that don't hit it and go by get through to the glass, thus forming the shadow. It could be either one. Now, pretend you're 150 years in the past. What two ways could you check to see if the rays were charged particles? We've covered some of this material earlier in the course, so hopefully you'll come up with some ideas. One rule, you cannot open up the glass tube. So please take a couple minutes and discuss this in your group. One idea would be to apply an electric field across the path of the rays. We've already seen how an electric field will exert a force on positive and negatively charged particles. So in this case, if you have charged particles, they will be deflected by the field. Here's our field right here. We have a positive and a negative plate, so the electric field lines go from positive to negative. Now, the direction that they get deflected will indicate whether they're negative or positive. And if they don't have a charge, we would expect them to go right through the middle and not be deflected at all. Or you could apply a magnetic field. And in this case, we have the magnetic field. See these red X's? And again, let's recall that means that the magnetic field is directed into the page, perpendicular to the plane of the page. If you have charged particles, they will be deflected. And it had already been shown earlier that waves are not deflected by magnetic fields. Also, the direction that they get deflected will indicate whether they are negative or positive.
Both experiments confirm that cathode rays are streams of negatively charged particles. Also, when different materials were tried for the cathode, the same results occurred. They were independent of the material. In 1897, J.J. Thomson used this experimental procedure of using magnetic and electric fields. Here's the electric field here between the red bar and the black bar, and all those X's are the magnetic field, to learn more about these particles. He and his assistants adjusted the field so they pushed the particles in opposite directions and canceled out, resulting in the particles going straight through like this.
What does this get us using the magnetic and electric fields at the same time? If you measure the magnitude of both fields, you can now compute the velocity of the particles. We start here with Newton, way back several hundred years ago. Sum of the forces equals ma. We then come up to the work that was done over the succeeding centuries, and we compare the magnetic force, which we showed is in the downward direction, and the electric force in the up direction. So when we balance the two fields so that the particles would go straight through, you have QVB, which is the equation for the magnetic force on a charged particle, where Q is the charge, V is the direction of its velocity, and we have QE for the electric force. So you have QVB minus Q equals 0. You put QE on the other side. You divide out the charge. It's interesting to note here that the charge does not figure in the answer. And finally, we get the velocity of the particles coming out over here after the magnetic and electric fields have been applied. The velocity would be the strength of the electric field over the strength of the magnetic field. Now let's see how J.J. Thomson and his team used all of these experiments. Again, we have a magnetic field and an electric field operating on these charged particles. And they found a very interesting property. First of all, they balanced the electric and magnetic fields. So you've got the electric field here, the magnetic field here, and you have the charged particles going straight through the tube. This enabled them to calculate the velocity of the particles as we showed on previous slides. Then they turned off the electric field. The particles were now deflected downwards because only the magnetic field is operating, and they hit a semicircular orbit and struck the side of the tube. So you're striking it somewhere down here. Once they found these particles in a semicircular orbit, they would see where it would make the screen fluoresce, and they would measure the radius of that semicircular orbit. Now we're going to go all the way back to Newton again, use his second law, and from that we're going to find out the ratio of the charge of these particles to their mass. Recall, the particles had a velocity which was equal to the ratio of the electric and magnetic fields. That would enable the particles to go straight through, and then they would be bent by the magnetic field. Remember, the electric field was turned off at this point. We now have the magnetic field exerting a perpendicular force. Now, we know what happens when you have a particle with a velocity and you have a perpendicular force exerted on it. It goes into a circular orbit, hence the semicircle that the experimentalists observed. We take Newton's second law, F equals ma. We now have a circular orbit, so we have centripetal acceleration, so A is equal to V squared over R. We know the magnetic force is QVB. We set that equal to mv squared over r. We do a little bit of algebra. We then substitute in the values for the electric field, which we know because we set it. The magnetic field was set, and r was measured by where the fluorescence occurred inside the tube. And after you calculate everything, you find out that the charge to mass ratio for these particles is 1.76 times 10 to the 11th coulombs per kilogram. This experiment showed that the particle had a very low mass for its charge. In fact, its mass per charge was 1,800 times less than the previous lowest amount measured for a particle, which people had been calling the hydrogen atom. And because that was, at the time, the smallest mass people found, they figured that was the smallest fundamental particle. However, we now have a particle that's 1,800 times in mass less than that. This led Thomson to propose that these negatively charged particles were something new, and he actually called them corpuscles. The name electron was taken from George Johnstone Stoney's work in 1874, and again by George Fitzgerald, who proposed it a little later, and that name stuck. Furthermore, since the electron was so much lighter than the hydrogen atom, it was concluded that it must be part of an atom, so there was some underlying structure here to the atom that had not previously been seen. Here's a replica of the Crookes tube used by J.J. Thomson at Cambridge University in the UK. Here's kind of the model we've been using, where the cathode's over here, The electron beam goes this way. Here's your electric field right here, which is deflecting the electrons. And then here's your semicircular orbit that they take once they're deflected by a magnetic field later on. Here's what it looks like in real life. Here's the dome, and on this dome is where you have the fluorescent material so you can see where the electrons hit. Thomson continued to refine his experiment, and here is a replica of the third mass spectrometer that he used. And you may have come across this in the magnetism chapter where we talked about a velocity selector, which is going to select out the charged particles with a given velocity. And then over here is where you have the magnetic field that will separate the particles out due to their mass. So the ions come from this side. The electrons are, the free electrons are created here. They go through the electric and magnetic fields where their velocities are chosen. They get bent, and over here we have a detector where you can find the different particles and what their charge to mass ratio is.